so let's say we have that. So what would you say the product of that would be? You guys want to take a few minutes or something, write out the product.
You would just attach your CH3O in place of the chlorine?
Chlorine, yep, exactly. Yep. So that would be your product. Exactly. Yep. Yep. All it is the so the lone pairs here, just like the SN2. This would attack the carbon, and then you take out the chlorine. So this is SN2. So because it is SN2, it's only going to occur on a secondary and a primary, right? It won't occur on a tertiary. So this is just, I mean, it's basically reviewing an SN2 reaction, but it talks about it again in Chapter 8 because Chapter 8 is all about ethers. So this is just a way that you can synthesize ethers. It's just kind of more reminding you what you've already learned about it. Okay? That's Lucas that asked that, right? Yep, okay. Yep, no problem, Lucas. Yeah, there seems to be, let's see, there's a problem here. 42. Actually, I'll tell you what, why don't you guys do 42? Kind of, it will review a little bit what we talked about yesterday. I kind of want to do a lot of problems, but what we talked about is a little bit here. So why don't we do 42? I have it up here. I'll make it a little bigger. Are you guys able to see it okay? So let me see. Do A through E. Yeah, do A through E, 42. All right, I'm going to put the video on pause. When you guys are ready, if you guys want to just put in the chat, say you're done, or I'm ready, or I'm set to go, this way I have an idea as to when we should start back, okay? Portal of the empty space. Let me get our... Okay. All right, so first of all, we said the 1-methyl cyclohexanol looks like this. OH there, and a CH3. Okay, so the first step is adding HBr, the first reaction. So the reaction with HBr and an alcohol, what it does is, if you think about the mechanism, the oxygen is going to protonate and it forms a water molecule, which eventually leaves to form a cation, and the bromine attacks. So this is a way to turn an alcohol into an alkyl halide. So that would be your product. Okay, and we did go over that mechanism. I believe we did it. This was chapter 7? That was the alkyl halide chapter. Yeah, which is in chapter 7. H2S, so that is acid. Usually you add heat to this. So in class I told you guys that they have to add heat to this. This is a dehydration reaction. Dehydration. And remember, this goes Zaitsev's rule. So we talked about this yesterday. I was actually very impressed that you guys know how to spell Zaitsev. So that was when we talked about it. So you're going to get the more substituted. And your double bond can either be going down, like how I have it here, or you could have drawn this molecule. It's the same molecule, have the double bond going that direction. So it's basically the OH is either going this way, or the OH is going that way. You can't form a double bond here, because that would be a least substituted double bond. So that is not obeying Zaitsev's rule. The next one, the CR03, that was a question that Jacob just asked. Since it's tertiary with CR03, there's no reaction. All right, remember, this is only done as Anna said, either on a secondary or a primary alcohol. All right, the primary would give you a carboxylic acid, because it's the stronger oxidizing agent. The secondary would give you a ketone. All right. Sodium. All right, so the sodium, let's redraw it over here. Remember, sodium metal, that was the reaction we talked about. I think it was one of the last reactions we talked about yesterday. You can either use sodium or sodium hydride. In this case, it's just a sodium metal. Deprotonates the hydrogen and gives you the negative charge. It gives you that strong nucleophile. That's how you form these negatively charged molecules. All right, so that's the product for D. And then for E, you're now taking this and adding it to methyl iodide. So this is an SN2 reaction, strong nucleophile, adding to a methyl iodide. So it's SN2. So this is the Williamson ether synthesis. This is kind of why we did this problem, because I had this kind of reaction. I figured it's a good review on everything. So that would be your product for E. All right. Any questions on that one? Good review. This is kind of what I want to do. I want to go over a bunch of these problems just to kind of review everything we talked about yesterday. It's just kind of to reinforce what we talked about. I think yesterday, I'm just reminding myself, I think we talked about pretty much the whole entire chapter. There are a few little reactions here and there that we'll talk about on Tuesday, but pretty much we have talked about everything in that chapter. So this is a good day to kind of now review all the reactions, make sure we understand all of them. Okay, so I don't see any questions. So let's kind of go back up and start doing a few of these problems. There's a few that I want to choose. That's basically what I want to do today. And then if there's any other questions you guys have, I'm more than happy to answer those. I have a question for dehydration reaction. Can you say again what reagents we're adding to identify as a dehydration? Yep, so a dehydration is acid and heat. All right, so let me just, and we can go over that mechanism again, because in understanding the mechanism helps you understand the reagents. It's basically a strong acid, okay? So remember we said acid, there's lots of ways how we show acid, either as an H+, or H3O+, or H2SO4, or H3PO4, or just saying the word acid. So these all mean all the same thing. So I like to just put H+ because it's easier to kind of go through a mechanism. But remember, anytime that you have H+, you also have water. Okay, so there's water in there. All right, so I did say that you usually have heat. Anytime that you do an elimination reaction, that's a weird looking heat. So this is an elimination because we're forming a double bond. Anytime that you form a double bond, it's a type of elimination reaction. Remember last chapter with the E1 and E2 stuff, E1 and E2, you remember we always added heat into all of them? So pretty much a standard, even though your book doesn't really talk about it, but I talk about it because it's true and you'll see it a lot, is that anytime that you use heat in a, you usually use heat in an elimination reaction. So you definitely have to use heat. So it's dehydration because the first step is protonating your alcohol. Give you a plus charge. All right, and that's the first step. And then we talked about that water is a good leaving group. So water is going to leave. Also, anytime you, in this chapter, in alcohols, anytime that acid is used as a reagent, this is the first step. It's always protonating the alcohol. And then the water leaves to form a carbocation. All right. And remember yesterday we talked about this mechanism is E1-like. Because you form a carbocation and then the water deprotonates a beta hydrogen. To form a double bond. Okay, so how do you know? So back to your question, what reagent? It's basically acid. I mean, all they're doing is adding acid here. In this other reaction, HB. You notice in A was HBr. You notice in one is H2SO4. So, all right. So yeah, Anna, you asked a good question. It's going more into the details. I'll talk about it since you asked it. It might actually help people too, because A is an acid and B is an acid. So how do you know that A, it turns into a bromine, and B, it gets eliminated? Like, how do you know that sulfuric acid eliminates and HBr forms the bromine? Well, one way is this thing that I told you. If you use any of those, it's implying that. But how do you know? So let's just kind of go over that since we're talking about it. There is something called a nucleophilic acid. And again, this is more information, but it might help you. Okay, a nucleophilic acid is where the anion can act as a nucleophile. So HBr is an example of a nucleophilic acid, because when it ionizes, it forms a Br minus. And Br minus is a nucleophile. It has a negative charge. It's just one ion, and it can act as a nucleophile. So in this case, when we have the alcohol and we add HBr, the mechanism is exactly the same. This alcohol is going to protonate, just like what we saw in the elimination reaction. And you form water, and then the water leaves, and you form a carbocation. All right? But you have Br minus swimming around. So the Br minus is going to act as a nucleophile. It sees this plus charge, and immediately it will add into here and form a Br. So this is SM1-like. Right? Because I formed a carbocation, and then my Br minus is going to add in there and form my alkyl halide. All right? So with the HBr, you actually form a bromine. The bromine adds on. The H2SO4 eliminates. So why is the sulfate not adding in as an ion? That's because that's not a nucleophilic acid. Okay? But first, any questions on this before I erase it, before I explain what a non-nucleophilic acid is? Okay. Okay, so sulfuric acid is what's called a non-nucleophilic acid because the sulfate ion, SO4 minus, is not a good nucleophile. So let's talk about why this is not a good nucleophile. You might think, well, it has negative charges. Wouldn't that make it a good nucleophile? All right, this is not a good nucleophile. You guys tell me, why do you think this is not a good nucleophile? Br minus is a good nucleophile, check, but this is not. All right, and remember, nucleophile is something that wants to share electrons. Why? So basically I'm saying these oxygens don't share their electrons very well because of resonance, exactly. Yep, exactly. That's always the answer, right? Anytime I say, why is this not good? Resonance, exactly. In fact, this has quite a bit of resonance. These lone pairs are preoccupied in the resonance of our sulfate ion. So this is not a good nucleophile. Same thing, you remember I said H3PO4 is also a good acid? The reason is because this is the structure of phosphate. All right, sorry about that S in there, just be a P. So again, this negative charge is preoccupied. All these minus charges are preoccupied in the resonance. So phosphate is also not a good nucleophile. So anytime you see H2SO4 being added or H3PO4, they're basically just saying this is just the source of H plus ions. There is not a nucleophile that is part of this. So in the HBr, you have the acid, but then you also have the Br minus to add as the nucleophile in the reaction. But with the H2SO4, it's strictly just being used as an acid in order to eliminate the compound. Because when you use the sulfate ion, let's go over this again. I'm sorry, the sulfuric acid. Okay, it's the H plus that's coming in here and protonating to form that water intermediate. The water leaves to form a carbocation, but I don't have a nucleophile. This SO4 2-, all right, will not add as a nucleophile because it's not a nucleophile. I don't have a nucleophile at this point. At this point, I have a plus charge, and all I have in here is water. And water, it could add into here, but it reforms the alcohol. So basically, at this point, the only choice it has is to pluck off one of these hydrogens and eliminate and form a double bond. Where in the HBr case, we have a Br minus swimming around. That can act as a nucleophile and add in there and form a bromine. Okay, so your simple little question, Anna, that you thought would be so easy to answer is all of this. But I think that might help. Okay, good. I'm glad that helps. Okay, so anytime that you do see this, if you see a simple acid, then, you know, so if this was HCl, the chloride acts as the nucleophile. If it's HI, it acts as a nucleophile. Pretty much any type of acid where you have oxygens that are part of the acid, so like nitric acid would also work, but usually people don't use nitric acid. HNO3, it's the same thing. The nitrate ion is not a good nucleophile, so it won't add in there. So any type of the oxyacids, if you remember from your Gen Chem days, oxyacids are acids that have an oxygen. It's usually the form of HXO. So like sulfuric acid, H2SO4, or phosphoric acid, H3PO4, or nitric acid, HNO3. But any of the monatomic acids, HBr, HCl, HI, those will act as a nucleophile. Okay? So that's kind of how you know that if you just see the sulfuric acid, then you know you're doing an elimination because you don't have a nucleophile that is part of that acid. All right, good. All right. So let's see. Let's do. I'm going to do a few of these problems. Oh, let's name it. Okay. Let's do. Let me get this out of the way. Let's do 33. Okay. I don't want you to do B because we have not talked about B. All right. We've kind of talked about D, but I want to see if you can figure this out. We didn't really talk about this exactly. Based off of what I just talked about between a nucleophilic acid and a non-nucleophilic acid, I bet you guys can figure this out. Okay. But definitely do A, do C, and then do D. As kind of the more challenging one. Okay. All right. Let me put this on pause. Okay, so the first one, we have a primary alcohol. So a primary alcohol with priodenane, which remember I said for short, we'll say PI. PI. So that's one of the weaker oxidizing agents, just like PCC. You get the aldehyde. You stop at the aldehyde. So that would be your product. Remember that there's only one carbon here. That's a carbon. That's a carbon. So that alcohol gets oxidized up to an aldehyde. It stops at the aldehyde. All right. Questions? Good. All right, C. Let me write this. Let me write it exactly how they have it there. So C, we have LAH. LAH is the stronger reducing agent. So it'll take an ester all the way down to the Remember, it's a two-step reaction. First step, second step. In class, I said acid. It can either be acid or water. Again, here's something where they tell you one thing in the notes and then they kind of change it in the end. But it doesn't really matter, acid or water. But the point is that this carbon right here, this carbon right there, is the carbon that becomes an alcohol. A lot of people always wonder, like, what happens here. If you remember yesterday in the mechanism, I talked about the hydride attacks into the carbon. So we have the hydride that comes in, attacks here, kicks up this pi bond, which then it pops back down and kicks out this whole entire group. So this whole group actually leaves. All right, so this carbon right there is the one that becomes an alcohol. So you have everything else. So you have CH2, double bond, CH, CH, CH3, CH2, and then this carbon right here becomes an alcohol, and you get two hydrogens on it. Charcoal color. So that's your product. Any questions on that? Makes sense. A lot of times people aren't sure what to do with all these groups. So it's basically the carbon. This is how you look at it. The carbon that has the carbonyl becomes the alcohol, and everything else that has an oxygen or something is gone. It's not gone. So this part of it becomes a CH3OH. All right, but that part we don't really care about. I just care about the molecule that has the carbonyl. So this becomes the alcohol. Okay, there's no questions. I'm going to erase that, and then I'll go over D, kind of a little more of a challenging one. So we have an epoxide, and then CH2, CH3, and you're adding HBr. Okay, so if you think about the mechanism with the alcohol, so prior to this I went over that whole mechanism where if you have an alcohol, you protonate the alcohol and it leaves as water, and then the bromine comes in. This is kind of the same thing here. All right, this oxygen is going to protonate. So I'm showing you a mechanism, all right, which is kind of like a mechanism that we talked about when we formed the trans diol in chapter 4. But rather than having an OH attack, you're having a Br minus attack. All right, so I have a carbon here and a carbon here. So this wants to break. All right, so your bromine is going to attack. Now, as far as our class is concerned, you can have your bromine attack either one of the carbons. All right, it doesn't really matter. In reality, it does only attack one of them, but we don't have to worry about it in this class. All right, so the bromine is going to attack one of these carbons, and it pops open this alcohol. So in this case, carbon 1 will have a bromine. I'll put CH2 here. The carbon right here, carbon 2, is going to have the OH, and because it's a transition, we talked about that in chapter 4, these epoxides are transitions. So you'd form something like this, where one of the carbons has a bromine, and the other carbon has an OH. All right, now if you switch them, if you have the bromine on carbon 2, that's fine if you did that. So if you have this, again, for our class is concerned, you can have it either way. If you are just dying to know which one is formed, it's this one right here. This is the one that forms. The bromine attacks the more substituted position. All right, but we don't have to worry about that. It goes into a little bit more stuff. But if you were able to understand that you get an OH on one carbon and a bromine on the other one, I'm very happy about that. If you didn't, don't worry about it. That's kind of why we went over it in class, so that you can kind of see, again, this is a nucleophilic acid. So basically the hydrogen is going to add on and the bromine is going to add on. All right, and understanding anytime that you have an acid with an oxygen, the oxygen is going to always protonate to form this type of a molecule, which one of these bonds are going to want to break. So the bromine is going to come in as a nucleophile, add on the one side, and pop it open. Okay, make sense? Any questions on that before we go on? Yes, good. All right, thank you. so let's do some synthesis. Let's do 34 and 35. Since lots of good synthesis problems. So 34 is show how you compare the following substances starting with cyclohexanol. So 34 is you're starting with cyclohexanol. Show me how to synthesize these compounds. And then 35, show how you compare the following substances from 1-propanol. All right, so starting from 1-propanol, so this is question 35, and this is question 34. So I want you guys to work on those. That's good. We said pretty much there's a lot of reactions from this chapter, from previous chapters. More than one step might be necessary. In some cases, you might only need one step. In other cases, you might need 2 or 3 steps. I don't know how many for sure. But I'll let you guys work on that. Okay? All right. I'm going to go on mute and turn off the video so you guys can concentrate. Okay, so we have, the first one is cyclohexanol. I'll do this. So to get to the ketone, we are oxidizing. So in this case, since it's secondary, you can use any of the oxidizing agents. So you can use PCC, or you can use PI, or you can use like CrO3 and acid, or you can use the Na2, Cr2O7 and acid. So any one of those 4, choose one, whichever one you put, that is the correct one. Okay? If it's secondary, you can choose the mild ones. These 2, PCC and PI, are the mild ones. Or you can use the stronger ones because you can't oxidize any further. All right? And then the Bromo Cyclohexane, there are technically 2 different reactions you can do. Either HBr, like we saw at the first reaction of the day, or you can add that PBr3. If you guys remember that reaction from the chapter 7, PBr3. So either one of those would be correct. So we have 2 ways of doing that. To form the double bond, that is a dehydration reaction. So acid and water in heat. Or if you wanted to put H2SO4, like what we talked about earlier, you can do either one of those. All right. Now, these are the simplest way of doing it. I mean, if you wanted to, what you could do is take the alcohol, turn it into the bromine, and then add a big bulky base and do an E2. So there's more than one way of doing this. I mean, the easy way is, it's just a one-step reaction. But if you turned it into an alkyl halide and then you eliminated it, that's totally fine also. There's more than one way of doing this. That should be a 3 right there. Okay, so if you did that, that's fine. And then D, in order to get the alkane, the best thing to do is to take the alcohol, do the elimination reaction and get the double bond, and then hydrogenate. So in this case, it'd be a 2-step reaction. You have to eliminate first, either with the acid and water, a dehydration reaction, and then hydrogenate, or you could have turned into the bromine, done an E2 elimination, and then hydrogenate. So either one of those is fine. All right. Any questions on that? Or did you guys do something else and you want me to see if you did it correctly? Because, like I said, there's more than one way of doing these. So if there's something else that you did and you want me to check, I'm more than happy to do that. Otherwise, if everyone's good, I will continue on. Okay. Next one, 1-propanol. Okay, so the aldehyde, if you want the aldehyde, you can either use PI or PCC. Either one of those. To get to the carboxylic acid, because it's a much it's beneficial to know all the options because the answer. But yeah, you're right. It does. It does. That's why I was trying to give you all of them. Yep. But that's also why, because you might have done something that I didn't think about, that it might work also. So that's why I kind of want to know what you guys are doing too, if you want me to check it for you. In this case, we're oxidizing up to the alcohol. The carboxylic acid. So either CO3 in acid, or you can add the Na2Cr2O7 in acid. Either one of those. You're going to use the stronger oxidizing agents. To form the O- with the sodium, you can either add sodium metal, or you can add sodium hydride. So either one of those would give you the same thing. We talked about that yesterday. And then finally, to turn it to the chloride, two ways, either HCl or SOCl2. In this case, SOCl2 would work better because this is a primary, and the HCl goes through a carbocation. So primaries and carbocations don't go great, but if you did it, it's fine. I'd be okay with that. Okay, any questions on those? On our next ones, you guys are typing. All right, let's do 39. It's another synthesis problem. So do 39. And then maybe we'll do one more. I like doing the synthesis ones. We see the most bang for our buck with those. And then we'll find another one or two after that. All right? Okay, I'm going to go on mute while you guys are working on that. Let me just make sure you do all of them. We've talked about all these reactions. Yeah, we've talked about all those. All right, so let's see, we're starting with 2-phenylethanol. So we have two carbons, ethanol. On the second carbon, we have an aromatic ring. And then on the first carbon, we have our alcohol. That molecule. So benzoic acid, remember benzoic acid looks like, so let me erase that. So the only way that we've learned how to make benzoic acids, there are several ways. One, oxidizing of an alcohol. But in this case, notice we need to cleave off carbons. That's the hint. We are cleaving carbons. We have to get rid of a carbon. So if you remember from chapter 4, the oxidative cleavage reaction cleaves a double bond, and it leaves a carboxylic acid. So that's going to be the reaction we're going to do. So in this case, it's got to be two steps. So, well, actually, I just thought about this. There's two ways that you can do this. So let me just do the way that I was thinking, and then I'll show you the other way. First way is to eliminate the alcohol with acid and water for a dehydration reaction to give you a double bond. And then you add KMNO4 in acid, which remember is going to cleave that double bond and give you a carboxylic acid. The other way is, if you just remember from the aromatic chapter, remember if you have a carbon, a benzylic carbon, that's sp3 hybridized and has a hydrogen, you can just add KMNO4 in water, and it will cleave all that off. So there are two ways. You can either eliminate it, and the reason why I chose this way, I mean, you can choose either way. Let me actually make that look a little bit better. Is because this double bond compound is going to come in useful for a few of the other questions. Okay, so you can do either one of those would work. All right, B, ethyl benzene. So ethyl benzene is basically what you would do is from this compound. So first you would have to eliminate to form the double bond, and then hydrogenate at this step. So hydrogen plus platinum oxide or palladium to get ethyl benzene. So that's also a two-step. So dehydrate the double bond. Now, if you again, you could have done the E2 elimination. You could have converted this into a bromine, okay, which is part C. So let's actually do that right now. Let's see. Let's kind of pull this arrow here. HBr, or you can add PBr3 to turn into a bromine. All right. So you turn into a bromine with HBr or PBr3, and then if you wanted to, you can add tert butoxide and heat. That's the E2 elimination from chapter 7. So lots of different ways of how to form this compound right here. You can either do the dehydration, which is a one step, or turn it to the bromine and then add a big bulky base to it to do the E2. Does that make sense? I know this is getting a little encumbered there, but are you guys following along? Make sure you guys are following. Isn't it PBO3? Yeah, so, yeah, Jacob. So, I was saying in class, you can use either one, but since you do have a primary, usually the PBR3 works better. But if you did HBr2, I'm fine with that. But yes, in reality, the PBR3 is what you use for primaries. And then the HBr is what you'd use for a secondary or a tertiary. But as far as I'm concerned, you can use either one. Let me clear this off a little just so we have more room. Does everybody have it? Make sure everyone's got it. All right, next one is phenylacetic acid. So you're oxidizing that up to the carboxylic acid, so CrO3 and acid. Or you can use the Na2CR2O7 acid to give you the carboxylic acid. And then the other one is an aldehyde. So if you want to go to the aldehyde, either PCC or PI. So I'm going to put pH here. So a shorthand for a phenyl ring is pH. That was right down here. So if you don't want to write the whole entire aromatic ring over and over again, a shorthand is just pH. So the way I would write that would be pH, and then my carbon, and then my aldehyde. So again, that pH stands for phenyl ring. So this would be a shorthand way of writing it. If you ever see like that pH, that's what that means. Okay, good. Questions on those? All right, let's find. I'd love to do all of these, but we just don't have enough time. Oh, this is actually I like 61. I just want to see what else there is in the cabinet. I'm looking for. Hold on a second. Let me see. Acidity, problems. Hamsters. Hold on, let me get this out of the way. All right, let's do 61. 61, that's a good one. And see where it says A, B, C, and D? It could be more than one step. It doesn't just have to be one reagent. You can add several different steps to it. So just keep that in mind. forgot to hit record when I did this, but here are the answers for that problem. Okay, so we'll work on 44, and then when we come back, we will go over those, and that'll pretty much be it for the day. That's why it's important to come to class, because the video might not be incredibly accurate. All right, CH3, CH3, CH2, and then the one that has the CHO on it, that becomes a CH2OH. That's where your alcohol turns up in that carbon right there. All right, in this case, you have 2 carboxylic acids, so which reagent are you going to use? You can't use one of them. So you can't use sodium borohydride, you have to use LAH in this case. And in this case, you get the dialcohol. Remember, those carbons are there. So you got to keep those carbons. The carbon right here, and the carbon right there. That's these carbons right there. And then finally, you have this compound right here. Sodium borohydride or LAH. So you get, let's see, 1, 2, 3. So you get CH3, CH2. You get a CH with an OH on it. And then CH2, CH3, HCH3. All right. Any questions? Otherwise, we'll call that a day. Thank you for coming today. Hopefully it was helpful. I think these days on Thursdays are helpful. We go over a lot of them. We go over some extra stuff.
Hey Steve, I do have a question.
Sure.
It was on 33, problem 33. We skipped B, and I'm wondering if that's something that maybe you could show the mechanism, or do we just not need to worry about that one right now?
For which one? B?
For B,
Yeah.
33.
Yeah, so I told you guys to skip that one, that we're not going to talk about that. Did you hear me, Lucas?
Yeah, I replied in the text box, but yeah, thank you.
Oh, you did? Okay.
Yeah, we'll skip it.
Okay. Yeah. Oh, whoa. Oh, wait. Oh, yeah, there we go. Oh, wow, just updated. That's weird. Oh, I'm sorry, guys. I missed all of these. I am sorry about that. I didn't even see any of that stuff. I don't know why. I think I had a glitch here. What does the book mean by R? Okay, Anna, did I answer that question? I think I probably answered that question.
Yeah, Lucas answered it actually, so
okay.
good. Thank you.
No, you know, I had my chat box up, but for some reason it wasn't updating. No, wait, yeah, MCPBA on step A. Let's see, Jacob asked on step A and D, is it okay to just put H plus? I think I probably answered that. Peroxy acid, yes, they're interchangeable. Lucas, Anna, thanks. Lucas, thank you. Okay, good. Sorry about that, guys. Yeah, if I ever, if you ask me a question, I don't answer it, I'd say within like 5 or 10 minutes. If you can either retype it, or why don't you say something on the chat, because it could be, again, I had to do something and it updated all this, so I missed like the past 15 things. So in the future, if I don't respond to you, if you can just ask it on the mic. But it seems like you guys are pretty good at helping each other out, which is great. So okay, so if there's nothing else, see you guys on Tuesday. Okay, I'll see you guys.